How's everybody doing? It's nice to be back at AutoSens. I know we're getting toward the end here, but hopefully can give you a little bit of something to chew on this afternoon and hopefully start some discussions. So like most people probably today, I've talked a lot about AI, especially on this track. I've called the talk AI inside and out. So traditionally we're talking about AI outside the vehicle, like ADAS features and those types of things, moving toward autonomous driving, but starting to be some pretty cool applications of AI in the cabin for interaction with the vehicle as well. So kind of first I want to talk about, even before we get down into those two pieces, just to show kind of an example of AI really being pervasive now in everything we do, not just once the vehicle's in production, but how do we get that vehicle to production, a bunch of uses of AI as well there. Then we'll get into the kind of details for the outside, then the inside. Finally, kind of talk just for a minute about how some of the hardware that's coming is really enabling a lot of this. And then leave you with some kind of summary and future work. All right, so if we look across the kind of the whole development cycle of specifically like an ADAS feature, even before right when the program starts, even before we start coding, there's a lot of AI tools now that are starting to help with a lot of the tedious things, a lot of the things that have a lot of human error prone, things like requirements management, BOM cost analysis. These things are starting to be much easier. When you get an RFQ that has 20,000 requirements, you of course want somebody to look at all of them before you sign on the dotted line, but to help distill those, summarize those, make sure you hit the big points early, really getting some cool tools around that. Then, of course, the code. I mean, you guys hear Copilot, GitHub Copilot, Claude Code, these kinds of things. These are a real phenomenon. We're not necessarily replacing developers, but helping developers, produce higher quality output faster. So lots of stuff even before we get to the car. And then the online systems. We'll kind of table this because we're going to talk about it throughout the talk. Simulation is another area that AI is doing some amazing things. So, I mean, for many years, we've used video game-looking simulators to practice our ADAS features and develop our ADAS features. There's this kind of persistent, what we call sim-to-real gap that we have to worry about when we do that. So the idea is if we train the model, if we test the model in a simulator, then we kind of cross our fingers, go outside, and see how bad the problem is that we have to fix once we hit real data. So to try to alleviate that gap, some of these AI approaches are letting you now use very natural language to augment and modify that simulated data, where you can kind of close that sim-to-real gap in a meaningful way. So number one, you can say literally, please make this more photorealistic, and it'll do that. Reflections get better, the textures get better. You can say add rain to the scene, and it will do that. So just tremendous variability now you can introduce in a very natural way into the simulation. And then we'll talk for a minute about the compute hardware at the end. So AI outside, this is kind of where I've spent most of my career, the ADAS feature development. I wanted to start with kind of a system overview and then a historical perspective. I think it's a very mixed audience here, so to make sure we kind of get everybody on the same page. So first, from a system perspective, you'll see people today break it down in various ways. The coarsest breakdown, I think you can say there's a subsystem for what we call perception. So perception system is responsible for taking sensor data and building what we call an environment model. It's important to note this is like a human concept. We'll talk about later why we may want to break down this concept a little bit. But this environment model is basically 3D bounding boxes. Where are all the objects? Polylines describing the lane model, that kind of stuff. Once we have that environment model, then the task is in automotive what we call drive policy, and other areas what they call prediction and planning. What do you do inside that model to achieve your goal? So if you're trying to get from point A to point B, you need first an environment model, then you think about how am I going to get to my goal. So with those two areas, you can kind of look at what's happened historically. Before about 2012 or so, this is what I'll call a traditional approach in both of those areas. So the perception, if there's any computer vision nerds like me in the audience, we were doing things like edge detection, SIFT features, those kind of things, very manually putting together how do these pixels seem to represent an object. At the time, that was fine. These days, that's kind of an archaic approach, and it's only been 10 years. On the drive policy side, it was what we call rule-based, and a lot of the production systems today are still rule-based. But rule-based, you think about this as a bunch of nested conditionals. So, for example, you take something like an emergency braking system. You say, all right, if there's less than 10 meters between me and the car in front of me, and my speed is closing at this rate, then apply the brake at this pressure or whatever. So it's this kind of very prescriptive sequence of events that needs to happen, things that need to be satisfied, and then events that need to happen. That's fine in general. You can get some pretty decent feature behavior in the kind of nominal case, but it's very hard to handle edge cases with that kind of thinking. So fast forward a little bit. So when you get past 2012, this was about when the convolutional neural networks hit the scene, revolutionized almost immediately the perception stack. So now we have these neural nets producing the object detections, but the drive policy basically remained the same. More sophisticated, but still the approach fundamentally is this rule-based idea. Fast forward to now, perception approach is changing, but not in such a dramatic way. Now we have foundation models and other things. The perception keeps getting better and better to the point where I'd say it's almost, not interesting anymore. That's not at least the bottleneck for a lot of these ADAS stacks. What is the bottleneck is kind of getting away from this rule-based behavior so we can get into much more complicated urban environments and things like this with our urban NOA type of features. So there are kind of two different approaches. One is just replace the drive policy subsystem with some AI, and I'll talk a little bit about that. And two is to kind of do what's more called an end-to-end system, where you actually let the network take the sensor data, go all the way through to these actuations, or at least to the trajectory plans, and maybe eliminate that kind of human intuition in the middle for kind of a positive outcome. Yeah, so I mean, let me just elaborate on that a little bit more. In the ideal case, right, in these kind of nominal driving cases, that environment model that you would imagine, okay, I know where all the cars are, I know where all the other pedestrians, bicycles, I know what they are, I know where they're pointing as far as their orientation. That's a very natural, fairly expressive representation. However, there's still a tremendous amount of what I'll call like information compression when you move from millions of pixels per time instant down to 15 bounding boxes. So when you get into these corner cases, some of that background information actually could potentially save you literally in a safety sense. So we want to allow the network to chew on that information as it's learning how to act in the drive policy subsystem. Think in your mind, things like what's happening in the background, parallax in the background, shadows, puddles splashing, especially when you start to have occlusion. Is there ways that we can kind of track the object even if we can't see it? So we're starting to see some incredible improvements coming by expressly not funneling the information through an environment model. So it's kind of interesting when you start to think about these end-to-end approaches. We don't have too much time here. I can't go into like a tremendous amount of detail, but I wanted to give you just one example of what does AI drive policy look like. There's a tremendous amount of context here that you need, so I'll try to give you like a 30-second lesson in what's called diffusion models. This is only one approach to AI drive policy, but I think it's a pretty interesting analog that's worth mentioning. So you may have seen image generation. So you go to ChatGPT or Gemini, Nano Banana, these things. You type in, show me a picture of a penguin, dancing, and it will do that. The way they do that is very counterintuitive if you haven't studied these methods. But what they do is they start with an image full of noise, and what they've done is they've trained these neural nets to progressively denoise that noise into the thing that the prompt says. So you can see on the left here, you start with this big mess of pixels, and then you eventually end up with this parrot. It turns out you can do exactly the same thing. In fact, researchers love to take an approach like this where they take a new problem, rather than coming up with a new solution, they just try to make the new problem look like an old problem, and then they try to apply the same solution. So that's exactly what you can do here with what's called a diffusion planner. You can start with, okay, here's my environment model. Now I want to basically generate noise as my future trajectories, and then I want to denoise those trajectories following the outcome that I'm desiring. So you can see on the right here, the left side is a big mess of these blue lines, and then you kind of successively refine these into the trajectory that you want. This has a lot of great properties. Number one, we've gotten rid of almost all the rule-based stuff, so that's kind of the goal. But we see better properties too, as far as smoothness, as far as more natural driving behavior, because it's learning this from the data rather than from a list of rules. So again, for time, I can't go into too much detail on any specific projects that we're working on, but what I wanted to do was just call out some of the kind of broader lessons learned or things to think about, the conversation this afternoon that you maybe can have around some of these points. The first one I just talked about, I'm trying to read some of this. So one thing that's really important is, these things come with the promise of simplification, reduction in cost, reduction in time. I think it's really important to pause that thought until you've actually seen it for yourself, because we absolutely are simplifying the system in some areas, but we're almost shifting the complexity, right? So instead of an army of software engineers, now we need half an army of software engineers, a quarter of an army of ML engineers, and a quarter of an army of data collection teams. So we're shuffling rather than simply reducing, but at the end of the day, we're hopefully getting a better outcome as well. So it's kind of an interesting dynamic there. What's also interesting to note is we don't have to, look at the literature and then go from what I'll call a fully classical system to an ultra-modern system all in one step. We can decompose the system and introduce some of these techniques, per module, per component, and that's really exciting because sometimes it's hard to take that huge leap. And if we can do this incrementally over a few model years, I think the rollout will be a lot cleaner. What's also interesting to note is this is like really a now thing. This is not wow, look at all this AI in the news, and what if we could apply it in automotive? It's absolutely not the case. I mean, even with the current hardware, I'll talk in a minute about the future hardware. These models fit. I mean, you can actually do this on consumer grade automotive compute hardware. So that's a really important lesson here. And then, it's always worth noting, this doesn't at all solve the safety problem. I won't say it makes it worse, but it leaves the safety and validation problem as a serious thing to consider. So, we're always keeping that in mind. All right, we'll switch gears a little bit to what I called AI inside the vehicle. In fact, you may have seen in cabin yesterday, one of my colleagues was talking about some really cool things they're doing with AI, other types of AI in the vehicle, where they're doing sensor fusion with the DMS cameras and the in-cabin radars and that kind of thing. What I'm going to talk about, though, is more on the vehicle interaction side. So I wanted to start first with the same kind of a historical recap. Maybe this one is a little bit less inside my domain's area of expertise. But first, we had knobs and buttons, right? You want to turn up the radio volume, you reach and you grab the knob and you turn it. If you want to turn up the air conditioner, you turns the temperature, change the fan. Everybody knew and liked that. Nobody knew anything better than that. At some point, touchscreens came out, right? And this is an example, I think, where sometimes the flash and an appeal of a new technology doesn't always solve all the problems. In fact, can introduce some problems. So with knobs and buttons, if you get in a rental car, you probably need to find the knob. But once you own that car for a while, you know exactly where the knob is, and you can keep your eyes on the road while you're adjusting something. When touchscreens came out, you basically now have to look at the screen even if you own the car, especially if you're on a little bit of a bumpy road. Everybody knows this kind of finger drift where you're trying to hit the button and it's kind of complicated. So, while it's a very powerful concept to put everything digitally on a screen, it's got some problems. It's not like the end of the car interface when you have a touchscreen. So, what can happen, and what has been, frankly, has been tried in the past. You've probably seen cars that accept voice commands, right? So in the past, it was like literally pattern matching for a specific command. You had to learn what your human had to learn what the car can respond to. It would be this kind of thing where you'd say, turn up the volume, and you'd kind of get this thinking, I'm sorry, I didn't understand you loop, a few times. So it never really caught on because it didn't work very well. But in concept, interacting with the car via voice is very powerful because humans are very good at talking while keeping their attention on something like a driving task. So if we can make that work, it's a pretty interesting idea. So, these LLMs these days really have solved the first part of that problem. So, I mean, understanding what you have said and then even, extrapolating that into what you intend or what you mean by that, more or less solved, right? And you've got good microphones in the car, so that part really isn't hard. Attaching that to the car functions, that's engineering work to be done, but also, not crazy. But I'll talk in a minute why, these architectures are really important about how you make a system really functional in that way. Something else, context awareness is pretty cool in these interactions. So if you imagine saying something I mentioned on the first one, rather than saying, please turn up the heat by 2 degrees, if you say, I'm cold, you expect the system to understand, I understand what that means. He's cold, he wants the heat turned up a few degrees. If it turns it up, you're still cold, you can say, hey, do it some more. Some very generic, abstract sentence like that is interpretable via this multi-turn conversation notion, where you can get very, very flexible and interactive, kind of almost literally a conversation going with the car. And again, for safety, we want to keep the human eyes on the road as much as we can, and this really helps to achieve that. So the interesting part here, though, is there are basically 2 competing things that you need to happen. One is you want ultra low latency. Nobody has any time anymore for you got to wait 2 seconds. You think the system's broken, you say it again, and then the system responds, and you're talking over each other. So ultra low latency, definitely super important. But you also need access to unlimited amount of data, through the internet for some of the types of tasks that you may want to do. So we want to combine these. So we want to do some kind of a lightweight LLM in the car that gives you that responsiveness. But of course, it's not going to be able to do the deep searching and the deep thinking with the giant LLMs, in the cloud. So we want to basically have a front end that dispatches to either the local or the cloud, and bringing those together is really what the challenge in this type of product design is. All right, so you may have heard last year NVIDIA and Magna have kind of partnered. We're now producing a dual Thor high-performance compute for the car. And really, that's going to unlock all of the kinds of things I'm talking about here. I'll show you in the next slide. I had even mentioned with the current hardware, we can actually do a lot of this, but if you look at this, kind of SOCs by the numbers, if you want to call this slide, you'll see some incredible jumps happening in this space. So if you look, I just took as an arbitrary reference a TI TDA4. That's got something between 4 and 8 tops, depending on the model. It's 15 watts of power. We've basically maxed out the level of autonomy we think we can reach on a system like that. So we can get some pretty decent highway driving, but as soon as you try to get into complex urban and these L2++ and you try to think about past L2, it's really, really tricky on some of the kind of 2026 automotive hardware. But look at something like these Thor platforms. You've moved from 8 tops to 2,000 tops. Right, so this is not some increment, what percent are you increasing? 10% more compute, what can we do? It's 250x more compute power. I mean, that is a jump that we've never seen, and will be an enormous enabler both for AI inside and out. Level of autonomy, we think we can push this. This is still not the same as a trunk full of H100s or something like that, but I mean, it's a tremendous amount of compute power in a traditional automotive context. And you can see that the power requirement, of course, goes up, but it goes up massively sublinearly compared to the compute power. So going from 15 watts to 100 watts, that's kind of manageable. For 250x increase in your compute power, definitely worth the trade-off. All right, so just 2 slides to leave you with. One, kind of some trends summarizing some of the things I just said, and then some kind of food for thought on the next slide. So first, these 2 things going down, the number of ECUs and the BOM costs kind of going down together in the sense of this centralized architecture that these big SoCs are enabling. That's enabling both things like sensor fusion. So on the perception side, those advances are getting enabled by this. Having enough compute to do some of this AI drive policy, having enough compute to do some of this AI LLM in-cabin stuff. Really amazing how these things are coming down quickly. The middle 2 things here I've showed these kind of, from a software perspective, things are merging. So not only if you look at the actual software architecture with these component diagrams, some of those blocks are starting to merge together and the lines are getting fuzzy between them. But also the domains are merging, right? So we've talked about this in-cabin stuff, this out-of-cabin stuff. We've got some work going on that how do we use that information together through what we call context-aware ADAS. These software systems are becoming intertangled in kind of a good way, where now you've got access to a lot more stuff at all the different times. And then functionality and performance going through the roof, right? So the levels of autonomy that we're pushing towards, the higher level things with hands-off and whatnot. These AI features, the capability per watt per dollar is just amazingly on a trajectory like we've never seen before. So just some takeaways from what I talked about today. The in-cabin stuff is coming. In fact, I just got back from Shanghai, and a lot of it's even in production vehicles over there already. Every car has its own cute little character that's your car assistant. So it's a matter of getting kind of consumer acceptance and costs down in the US-Europe market until you start to see that here. But the technology is there. Diffusion models, not specifically, but more generally, AI drive policy and these end-to-end networks are, making their debut. So in the last couple of years, we've started to see this kind of stuff come out. This is all consumer automotive, which is really an amazing change. These new hardware platforms, we just talked about that on the last slide, so we don't have to dwell here, but are really the enabler. Let's not forget about safety. So all these approaches are great, but we need to keep, from a validation safety analysis perspective, we need to keep the pressure on there. And then again, just to close that, this is happening now. So I'm really excited about that. I hope you guys are too. If you're working in this space, I hope you have fun with me. If you're driving these cars, I hope that's a good experience for you as well. And I look forward to the discussions this afternoon. Thank you. I think we have a few minutes for questions. Yeah.
Thank you for the really interesting talk. I'm Samson Melamed, the principal research scientist at Code Metal in Boston. And nice to meet somebody else from Boston, also in the automotive space. So we work on really translating from prototype code into production code and helping customers to accelerate through the bottom of that engineering V. And one thing we've seen is, we're primarily working in the defense space. There's a real hesitancy to end up, vendor locked with, let's say, just with NVIDIA. And so we're often doing things to help customers convert from CUDA into OpenCL. And so your slide showing the Thor, the performance was absolutely incredible. I'm curious, do you see the same type of appetite inside the automotive industry to be, I guess, not so much vendor locked into one specific solution, but to be more platform agnostic?
Yeah, it's an interesting problem. It's been there even before the AI stuff, right? I mean, we call this generally SoC portability. So there's always different ways the memory is managed. Now these accelerators are different. The things like CUDA is definitely is a real problem. It would be wonderful if we could decide which vendor to use for the hardware separately from the software development, right? We simply can't do that these days. There are a lot of commonalities. I mean, it's usually possible to understand if it would be possible to port, but the porting is still kind of an annoying engineering task that unfortunately takes a lot of time and dollars. So it's a real problem. I think it's getting better. People are starting to take that problem very seriously, and the people who are buying these chips are starting to demand more as far as we know where we're going to get locked in, so let's not do that. And then the vendors change their behavior a little bit. So it'll take time. It's all fairly new, but it's a good point. Yeah.
Thank you for your talk. My question is around the LLM interaction that you were speaking to. The industry was seeing this almost migration back to buttons, right? We realize screens suck.
Yeah.
People don't like them. Let's get buttons back. And I think AI is kind of disrupting that to say, no, now I can interact with it. I think the main issue there is reliability and problems like hallucination. Have you been part of conversations where we start having, the fit rate type reliability metrics allocated to AI, and then that's the validation? Or do you see this tech being so revolutionary that people don't care? And are we going to do screens 2.0 with AI?
Yeah, I mean, as far as the hallucinations, I think the what I call the edge stuff versus the cloud stuff. The edge stuff, I think, is much harder to hallucinate. I mean, those are smaller models doing simpler tasks with literally a vocabulary kind of output. So you're not going to get, hey, please turn up the temperature, and then the windshield wipers start turning on. I've not seen that type of error. When you, of course, go to the cloud and you say, hey, find me a coffee shop that's on my way to the office and that has vegan options, right? Then you may get some weirdnesses, and I think those are much more tolerable, and people are frankly used to those kind of errors through the the AI on their phones and in their house. So yeah, TBD about consumer acceptance, right? I mean, I think you do some pilot studies or something, but until you really launch these en masse, it's hard to say what people think about them, which things people use, in any kind of statistically meaningful sense. And just getting used to the system too will change your behavior with the system. So screens 2.0, maybe. I mean, nobody's removing the screens for the sake of this LLM interaction, right? It's kind of a combination. So I think it's all uncharted water, but it's a very powerful concept that I think should probably be there in some way. The question is, exactly how. That's what we need to find over the next few years.